Good afternoon. It is now 2 o'clock, and so we'll go ahead and get started. Welcome to another CIRI webinar series, and thank you for choosing to share some of your time with us today. For those of you who don't know me, my name is Elena Buss, and I'm a Senior Research Program Manager for the Critical Infrastructure Resilience Institute, a DHS Center of Excellence housed at the Granger College of Engineering's Information Trust Institute here at the University of Illinois. I'll be the moderator for today's talk, and before introducing our speaker for this session, I'd like to give a couple reminders. Please mute yourself during the presentation. We will have time for a Q&A session at the end of the talk. At that time, I will invite participants to unmute themselves to ask questions. If you have a question and would rather not unmute yourself, please feel free to throw your question in the chat. The chat will be monitored throughout the presentation. This session is being recorded and will be available a short time after the presentation on the CIRI website. And finally, the research from today's presentation was funded through CIRI by the Office of University Programs out of the Department of Homeland Security. So without further ado, it is my pleasure to introduce our speaker for this afternoon's presentation on assessing risks of 5G, comparisons across end-to-end elements of interdependent system risks, Dr. Iris Tien. Dr. Tien is a Williams Family Associate Professor in the School of Civil and Environmental Engineering at the Georgia Institute of Technology. She joined the faculty in 2014 after receiving her PhD in Civil System Engineering from the University of California, Berkeley. Dr. Tien's research interests are in probabilistic methods for modeling and reliable assessments of civil infrastructure systems. She has a unique interdisciplinary background that encompasses traditional topics of civil engineering, sensing and data analytics, stochastic processing, probabilistic risk assessment, and decision-making under uncertainty. Her work on interdependent infrastructure systems modeling and analysis has twice won first-place paper awards in resilient critical infrastructure. Dr. Tien's research has been funded by the National Science Foundation, Department of Homeland Security, U.S. Department of Transportation, and National Institute of Standards and Technology. Dr. Tien has been selected by the National Academy of Engineering to participate in 3 Frontiers of Engineering Symposia. She was also selected to organize a session on resilient and reliable infrastructure at the U.S. Frontiers of Engineering Symposium and speak on community resilience at the National Academics Frontiers of Science, Engineering, and Medical Symposium. I'm delighted to now turn it over to Dr. Iris Tien. Dr. Tien, welcome.
Thanks very much. It's my pleasure to be here today to talk to you about work that we've been doing as part of this project in assessing risks of 5G, looking at comparisons across end-to-end elements and also interdependent system risks. So the motivation behind this work is that we know that telecommunications is becoming increasingly connected to critical infrastructures. So as an example, telecommunications is connected to energy, transportation, water, increasing amounts of critical infrastructure systems and functions. And so what we want to do with this project is to identify risks across end-to-end elements of the telecommunication system. And we're really going to be focusing on the transition to 5G for the cellular network and really the use of 5G for increasing asset automation and control. What we want to do with this project is to be able to comprehensively analyze these risks. And we're going to do this by creating a framework that is able to quantify the impacts of risks. And by quantifying it, we're creating the ability to also compare different risk elements. And something else that we want to do with this project, which is a little bit different from what's been done before, is we want to also be able to evaluate impacts of telecommunications systems risks on connected critical infrastructure functions. And so rather than just looking at the system itself, we want to be able to understand risks on interdependent infrastructure systems. And the overall objective here is to have an increased understanding of this full risk profile of 5G and to be able to better protect critical infrastructure functions that rely on 5G for asset automation, monitoring, and control. There are 3 main areas that we are advancing compared to current best practices or current state of the art. The first is that if you're working in the space, you know that there's a lot of entities that are currently evaluating telecommunications risks, specifically 5G risks, but many of these look at individual elements. So they look at implementing a certain security protocol or developing a trusted supplier process or trusted supplier list. And in comparison to these efforts, we are looking to be able to comprehensively assess risk across multiple different elements. So we want to include both physical as well as service-based elements, and we want to be able to compare and assess these within a single framework. The second main area that we're looking to advance in is rather than qualitative assessments of risk, so many of the current studies or information available provides risks in a qualitative manner, something like low, medium, high. And instead of having these qualitative assessments, we are wanting to be able to have a quantitative assessment of risk, including quantitative measures of risk impacts where available, to also facilitate this comparison across different risk factors. Then finally, rather than focusing solely on telecommunication systems and the telecommunication system and the risks associated with the system, we want to characterize the impacts of telecommunications risk on connected critical infrastructure functions. So looking beyond the single system, looking beyond just 5G, and looking at how 5G risks might impact other dependent or interdependent infrastructure systems. So the outline for the talk today is going to be in two main parts. The first main part is going to be a broader risk assessment for 5G. I'm going to talk about how we've built a risk profile for 5G and how we're looking to quantify the impacts of risks, including risks that affect the public both directly and indirectly, and then provide some information that enables us to do some comparison across multiple risk elements. And then the second main part of the talk is going to be looking at an interdependent system case study. So I'm going to talk about specifically, we have been looking at the transportation system, and so looking at 5G and the connected transportation system. I'm going to talk about how we define and then also vary different analysis parameters in the study, and show results that enable us to compare the different quantitative impacts across different risk scenarios. And so there's going to be different risk scenarios that we're going to look at between 5G and the connected transportation system, and I'll show results that enable us to compare those risk scenario impacts. So let me go ahead and start with building the risk profile of 5G. And so this was what we did was to integrate information that we garnered and collected from different stakeholder interviews to build out the risk profile of 5G. And what we wanted to do here was to identify the different risk elements that exist and also form recommendations for corresponding risk mitigation measures. And so here's a figure that shows the different risk elements that were identified. This includes physical hardware, software security, third-party developers. The next two risk elements going down the line here is looking at connected devices and critical infrastructure. So this is something that's a little bit different than what's been done in the past in terms of this idea, again, of looking beyond just the telecommunication system itself and looking at connected devices, what risks are introduced into the system from those connected devices, as well as the connections with other critical infrastructure systems. We also identified legacy equipment interoperability, supply chain risks, and also unknown risks as this new technology develops and is expanding. And they are mapped to different mitigation measures shown on the right. But what we wanted to do with these risk elements then is, so we have different risk categories that these elements belong to. These are related to the CISA risk categories, as well as connected devices risks, looking at those devices that connect and rely on 5G. And within these risk categories, we want to characterize specific potential risk scenarios and identify consequences. So there's going to be specific scenarios that we can look at, and we want to identify and also quantify the consequences of those risks. And so to be able to do that, we are quantifying the impacts of those risks by looking at different aspects of each risk scenario. So we're going to consider 4 aspects for each risk scenario, and I'll go through those right now. The first is looking at the expected number of people affected. So for a given risk scenario, you can imagine that depending on the range of the risk, the range of the severity of the scenario, you might have a different number of people that would be affected. So we want to, this would definitely be a quantitative measure that we want to obtain to see how widespread is this particular risk scenario. The second is looking at the probability of occurrence. So we can have very likely events, we can have very unlikely events. We might have these low likelihood events with large impacts, or vice versa as well. So we want to include probability of occurrence as a measure. We are looking at severity of impacts as well. And so this is a case where it's difficult to have a quantitative measure. So we have defined different severity scores here from 1 to 5, looking from very low to severe, a very high severity there. And then finally, we want to look at also the time required to restore full service. So this is another quantitative measure that we can use. This is really looking at recovery time. So if we're looking at resilience of infrastructure, how fast is it to recover? How long does it take to recover? This measure addresses that and looking at the time required to restore full service. And we'll note that it includes the time that's needed to detect a problem. So for example, for a cyber attack, all that time is included in that time measure. And so for all of these four aspects, we are using quantitative estimates where available. So as much as possible, we want to be quantitative where possible, but qualitative scores are used where necessary. In characterizing these different risk elements, something that we found was that we do need to distinguish between risk elements that affect the public directly versus indirectly. So as an example, risks that affect the public directly are potential telecommunications attack or malfunction scenarios. In comparison, some risks that affect the public indirectly is dependence on parts from overseas suppliers. So in this case, the effects of these risks impact the public more indirectly. And so for these latter risks, these indirect impacts, we still want to have a quantitative measure of the risk impacts and consequences. But what we're going to do is transition from expected number of people affected. So number of people affected will be relevant to the ones that affect the public directly. And we're going to use an expected economic impact as a measure of the risk impacts and consequences for the risks that affect the public indirectly. So now I'm going to go ahead and show the results that we are building out now to be able to facilitate comparison of these risks. So let me first start with the risks that are affecting the public directly. And so here we've plotted in a 3D plot here varying aspects of each of these risk scenarios. So each of these points here is a different risk scenario. What we show here are the expected number of people affected, that's on one of the horizontal axes, the severity of impacts, which is on the second horizontal axis, the expected time of reduced service is on the vertical axis, which is, you can also think of as recovery time, and the probability of occurrence is denoted by color there. And so this is something, I will say this is something that we're continuing to build out, and we've relied on kind of existing information or information that we're able to find to quantify these measures where we can. So a few statements about this approach and the results that we can show from it. And so what we wanted to do was to show the various aspects of each risk, and wanted to actually keep those various aspects separate so that you can have a better sense of the full risk landscape to give a more comprehensive view of the full risk landscape. And so by keeping those different factors separate and also being able to put numbers where possible on these different risk aspects, it allows for a better understanding of which risks are of concern and why. And so as an example, if we look at the malfunction of a single antenna, so that's that red point in the middle there, it has the highest probability of occurrence, and it has relatively long recovery time, but moderate severity of impacts. And so what we can think about there is that while the range of a single antenna is fairly small, and so relatively small number of customers affected, but maybe the long recovery time is the part that you can improve the most to reduce this risk. And so maybe determined that speeding up the repair process would be the most effective mitigation factor, mitigation effort for this risk scenario. So you can think about kind of balancing between different risks here. Based off of the different factors, you might also suggest or recommend different risk mitigation measures, and it enables this comparison across multiple different risk scenarios. So now that I'm going to talk about, in a similar way, we've looked at risks affecting the public indirectly. So we have a similar plot here. Now, instead of the expected number of people affected on one of the horizontal axes, we're looking at expected economic impact. And so we have these different risk scenarios, again, plotted on this 3D plot, which we show expected economic impact, severity of impacts, the expected time of reduced service or recovery time, and then the probability of occurrence by color. And so similar to the previous plot, but now with a different set of risks, we again show the different aspects of the risk separately so you can compare them across varying risk quantification measures to allow for this better understanding of which risks are of concern and why, and being able to do this comparison across different elements. So compared to what has been done before is really getting a comprehensive view of these different risks, being able to quantify them and measure them in terms of these different measures that we've defined. And I will say there's many risk elements in this landscape, in this whole risk profile. So this is some ongoing work that we're doing to continue to characterize and plot out these varying risk elements for analysis and also for comparison. All right, so that is the approach that we're taking for this more comprehensive view of 5G risk and the different risk scenarios that exist. Now I'm going to transition to looking at our interdependent system case study. And so what this is looking at is, so we have our category of connected devices risks. And so if we care about the connected devices, what risks does that impose on the telecommunication system, and also the other direction in terms of what risks of 5G can then impact dependent systems. We're going to look at this interdependent system case study. We've chosen to look at the transportation system and connected and automated vehicles in particular, and really kind of broadly speaking, there's many high-stakes applications of 5G technologies, so it's really essential to be able to evaluate the consequences of a potential failure in the telecommunications system on these interdependent systems. And so the work that we're doing as part of this project is to consider the impacts of 5G risks on the transportation system, including connected and automated vehicles and smart transportation infrastructure. We are going to consider both privacy risks and safety performance risks with this interdependent system. Here's a table showing the different aspects that we're considering for both the privacy risks and also the safety and performance risks. On the aspect column, you can see we have probability of occurrence, similar to before. We have expected duration of the event. And now we have expected number of vehicles affected as our measure instead of people affected or economic impact. Since we're looking at a transportation network, we are quantifying it based off of the expected number of vehicles affected, and then also the severity of the consequences is something that we're interested in as well. I will draw your attention to the safety and performance risk. These bottom two entries in this table here is we want to look at the number of vehicles whose travel time increased or had increased stop time, time stopped due to traffic, increased traffic, or number of collisions. And these are going to be the quantitative measures that we're going to want to be able to obtain to be able to quantify some of these safety and performance risks. And these two entries here are going to be from simulations that we've developed and conducted as part of this project, and I'll go into more detail about these simulations in a second. But before we go into those safety and performance risks, I want to talk about the privacy risks that we've looked at as part of this interdependent system case study. So here we have three privacy risks that are listed. It's side channel attack, passive man in the middle, and the location tracking. And so here we have the three privacy risks that we've identified, plotted with expected duration and expected number of vehicles affected. We have a severity score and also probability of occurrence. The main takeaways from this is that these are all variations of different eavesdropping types of attacks. They have similar probabilities of occurrence and severities, and they also have relatively short duration. And they're typically pretty targeted attacks, which affect or are expected to affect only one or two vehicles each. So we wanted to include these to give kind of a comprehensive view of the risk landscape. These maybe aren't quite as interesting as some of the results that I'll be showing coming up in terms of safety performance risk, but I did want to show these to give a sense of also the privacy risks that exist. So with that, let me go ahead and transition to those safety and performance risks that I talked about. And so here we want to look at the impacts of 5G risks on safety or network performance. And we're going to do this by taking a simulation approach. So what we're going to do is we're going to build out a transportation network, build out 5G, build out how it connects between the two, and then we're going to conduct various simulations. So we're going to look at simulating various telecommunication system failure scenarios and analyze the impacts on that dependent transportation system. So we're going to simulate those different telecom system failure scenarios and then look at the impacts on the transportation network. In these simulations, we need certain outputs that we are going to use to quantify the severity of impacts. And then again, once we have that quantification, then we can also compare then across multiple different risk scenarios. So we're going to look at 4 different outputs as part of these measures of impacts. The first output that we're going to look at is what we call time loss. And so this is going to be the time added to a particular vehicle's trip from driving below the ideal speed limit, so kind of how much time is lost in the network due to this particular 5G risk scenario. We're going to also look at stop time, which is the time spent completely stopped on the road throughout the trip. So this is kind of increased in amount of time that a vehicle is stopped in the network due to some sort of 5G attack or 5G risk scenario. We're going to look at number of collisions and then also the number of vehicles affected overall. So this is going to be any vehicle that has an increase in time loss, stop time, or has a collision. We're going to count as part of the number of vehicles affected. So these 4 outputs together are going to give us a sense of the quantitative impacts of a given risk scenario on the transportation network. And so when we have these outcomes, what we're going to do is we're going to look at the different risk scenarios, look at those impacts with these 4 measures, and then we're going to compare that to a default scenario. So this default scenario is going to be a no failure, no attack scenario. Everything is running well. That will be our default scenario, and then we'll have these risk scenarios where we have potential attacks or potential failures, which we can compare those impacts then to the default scenario to see what the increase in risk impacts would be for each of those scenarios. So now to talk a little bit more about the workflow for our simulations and our analysis. So we conducted this simulations using these 2 programs, Sumo and Mosaic, that are put out by Eclipse. And what this does is we can integrate both 5G parameters and also transportation network parameters, and include those parameters in our simulation outcomes. So as an example, we take an example of road network, some segment of the road network here. We input into the program, and then we define the parameters that define the characteristics and routes of the vehicles in the scenarios. And then we also have our simulated vehicle to vehicle as well as vehicle to infrastructure 5G communication. And so we have both the vehicle inputs as well as the 5G communication inputs for both vehicle to vehicle and vehicle to infrastructure communication. And then what we do is we input a parameter change that simulates an attack or a malfunction event. So we have built this network, and then we can change parameters to simulate one of these risk scenarios. And then the outputs from this would be vehicle position, speeds, collisions, and congestion, which we'll be able to use for our 4 quantitative measures that we're going to use for risk impacts. So let me talk now about some of our simulation parameters. So we are taking a 1,000-second long simulation here. We have a step size of 1 second. And one of the things that we wanted to look at was something that's in the relatively near future. And so we have a combination of both automated and non-automated vehicles in our network. We have a 50% split right now in terms of automation and non-automation. So this is kind of simulating a relatively near-term scenario where we have this mix of vehicles. Not everything is completely automated yet, but we do have some integration of automation. Here is a schematic of our vehicles and then our roadside units and our server. So the vehicles have vehicle-to-vehicle communication, the ones with automation that is. They can communicate with roadside units, which we're abbreviating as RSUs right now. And then the roadside units also communicate with the server. And I'll talk about each of these different elements in a little bit more detail in a second. But overall, the idea is that vehicles periodically broadcast messages, which are called CAMs, and I'll talk about these messages on the next slide in a little bit more detail. But essentially, the vehicles broadcast messages that contain information about themselves and sensor data about their surroundings to other vehicles and the roadside units that are within the range. And then the other vehicles can react appropriately to this information. And then the RSUs forward the gathered information to the server, which has a larger overview of the network. And then the server can then send certain messages. So, for example, these warnings here, which I'll talk about on the next slide as well, in terms of a type of message that can be sent. And so the server can then send messages to vehicles of different hazardous conditions or traffic in their vicinity, and the vehicles will also then respond accordingly. So I talked about 2 different types of messages. So in our simulation, we can include both types of messages. The first are these CAMs, which are these cooperative awareness messages. And so this is going to be a message from an individual vehicle. It includes the vehicle's location, speed, acceleration, direction, the vehicle type, and size. And so the messages are sent to all vehicles, of course, only the vehicles with these vehicle-to-vehicle or vehicle-to-infrastructure capabilities, and RSUs within the sender's broadcast range. And so it's sent from the vehicle to other vehicles within the range and also to the roadside units. And then we also have these decentralized environmental notification messages, the DENMs. And so these are kind of broader over the whole network. It contains information about potential hazardous road conditions or unusual traffic conditions. So road conditions could be weather-related, like fog, ice, or rain, or unusual traffic conditions. And so these messages, it transmits the type of hazards and its location to the vehicles that are within a radius of the hazard. And so the driver can be notified, and then the vehicle can respond automatically by either rerouting, slowing down, or changing lanes. And so in our simulation workflow, we include both of these types of messages. And we'll also, in some of the risk scenarios, we'll look especially at the environmental notification messages as a potential risk scenario. So let me talk about now the 5G network parameters. And so here are the parameters that we've set for the 5G network, kind of based off of best practices and what exists right now. So we have max uplink and downlink bit rates here. We have a 3 millisecond latency, 99.999% reliability for the network, and a packet loss probability of 0.08%. And so we took these values for previous studies that we've seen for vehicle communication type applications. I will note that these network parameters can be adjusted. These are kind of the default ones that we've put in right now for the simulations. The second thing that we need to look at for building out the 5G network is looking at the roadside unit placement. And so there's no specific guidelines that exist for where you should place roadside units. As these systems are being deployed, people are kind of figuring this out right now. So there's not kind of one standardized way to place these. coverage of a given unit depends on a lot of different factors, like installation height, if there's a sharp curve in the road, and the number of lanes, if there's any obstacles that surround the unit. We are looking at an urban area for our study area, so with a fair amount of congestion here. So for an urban area, you can place them uniformly through the network, or specifically in an area with a high vehicle density. So what we've done for our study is we've evenly distributed our roadside units throughout the network, and we're looking at installing one at every intersection to cover the whole network. And the blocks in the network are roughly about 100 meter by 100 meter. And so that's how we've decided to place the roadside units in our network. Again, this could be changed if there's a different, let's say, a pilot deployment that's out there that we want to assess the risks for. We can also adjust where the roadside units are placed, how far apart they are from each other. So now let me move to the vehicle automation. So here we have the icon of that automated vehicle with communication capabilities here. So here we're looking at 5G-enabled vehicle automation. At the very start of the simulation, it activates a vehicle distance sensor that can detect the distance with the vehicle ahead. The range of the distance sensor is 4 meters. And then at every time step, we are broadcasting a CAM, so that cooperative awareness message, to all vehicles and roadside units within a certain radius. This radius can range, so we've chosen a 400 meter radius here. And then it can also facilitate emergency braking. So if the distance to the vehicle ahead is decreased by a certain amount, essentially by more than 7 meters in the last time step, which would be 1 second, and the distance to the car is below 15 meters, then it activates this emergency braking. So there's this emergency braking capability that's facilitated by this automation. Looking at the roadside units now. So here, the roadside units forward messages from the server out to any vehicles within their range. In several of the following risk scenarios that I'll talk about, roadside units can forward information about certain hazardous conditions. We are considering this as a potential risk scenario in the sense that if there was an attack on the roadside unit and false hazardous conditions were reported, we want to look at what the impacts on the network would be. And then finally, looking at the server here, the server acts as a traffic management center and has information about a wider network than the individual RSUs do. And so what it does is it processes information received from the roadside units and sends the decentralized environmental notification messages to the relevant roadside unit so that it can warn the vehicles in the vicinity. So there's that location-based element there where it's sending the messages to the roadside unit that's around the hazard so that it can then warn the vehicles in the radius of that roadside unit. There is one note that latency is increased when a message has to travel from the vehicle to the roadside unit to the server and back. So there are certain efforts that are being made to do the prioritization of risks at the roadside units. In our case, we have these messages coming from the server. So what I wanted to do here is show a bit of a visualization of what our simulation looks like. So here is the road network, our example road network that we're looking at. Each of the little squares are vehicles, and then if you can see, some of the squares look like roadside units. Those are the ones at every intersection. And so the vehicles enter the network and they travel through the network. I'm going to go ahead and play this animation now. What you can see is the colors changing are the vehicles sending or receiving messages, or the roadside units sending or receiving messages. And so when it's a green box there, or let me start with the red box there, it means the vehicle is sending a message, or the roadside unit is sending a message. And then when it turns green, it means that the nearby vehicles or nearby roadside units are receiving that message. And so you can see this evolution of the network in time. The time step of the simulation is 1 second. So every 1 second, vehicles are receiving and sending messages, and then they're also moving through the network 1 second at a time. And so you can see this is a dynamic process. The vehicles are changing where they are, sending and receiving those messages over time. Let me go ahead and let this animation finish here, but you can definitely see kind of how this distribution is occurring over the network. All right, so this is how the simulation works. And so now what I want to do is show results from the default scenario, and then talk about the risk scenarios that we've looked at and compare the results there. So again, the default scenario is this no risk event scenario. So this is everything's working properly. There's no attacks, there's no malfunctions. For that 1,000 second long simulation, we have 650 vehicles in the network over the duration of the simulation scenario. And then the outcomes that we're going to get are distributions of certain outcomes over all the vehicles. We're looking at time loss and stop time. So if you remember, time loss is the amount of time increase in time for the trip due to traveling at a lower than ideal speed. Stop time is the amount of time that the vehicle is stopped. And we're going to show this as a percent of total trip time. And so here are the examples of the outcomes from this default scenario. So on the left here, you can see a distribution of the time loss. So you can think of this as a histogram of the distribution of how much time is lost for the network. And then on the right hand is for the stop time. So this is showing the outcome for all the vehicles in that scenario. For the stop time, you can see a big bar at 0. So on that very left-hand side of the stop time plot, you have a high bar there. So that actually shows 0 stop time. So that means there's 0 extra time that's stopped, which is maybe what you expect. And if the network is operating as it should, and there are a fair number of vehicles that can go through without having any extra stop time. But then we also have this distribution of increased stop time. And then so from these distributions, we're going to extract certain quantitative measures. So I've shown the table of quantitative measures that we're going to look at. So I have indicators listed there, and then the value. So the first two are mean stop time and mean time loss. And so this is 38% is the mean stop time. Again, this is a percent of the total trip time. And then the mean time loss is 70%. So this is a relatively dense urban area. There's a fair amount of congestion here. So the trip might take 70% longer than you might expect if there were no vehicles. You're by yourself on the network. You can travel at your ideal speed. So in this congested network, then we have this mean time loss of 70%. The percent of vehicles affected isn't applicable for the default scenario, but we will have an increased percentage of vehicles affected in the risk scenarios. The next 4 items in that column are looking at the percentage of vehicles that are greater than 2 different thresholds. So we're saying greater than 80% stop time or time loss, or greater than 95% stop time or time loss. And so what this is trying to measure is perhaps what we care about is these very extreme cases where you have huge impacts on vehicles, and we want to see what proportion of the vehicles fall in that extreme category, this kind of very high stop time or very high time loss category. So those percentages will show there. In this case, it shows a very small percentage have greater than 80% stop time, 0.3%, and then 22% have greater than 80% time loss. And we'll see how these numbers change under the different risk scenarios. And then finally, we'll have a vehicle that didn't enter the network, and I'll talk about that measure when it's relevant in some of the risk scenarios. So this table is going to be shown for all the risk scenarios, and we can compare these numbers for the default scenario compared to the risk scenario numbers. So with that, let me go to the risk scenarios that we've looked at. So there's 3 main ones that we've looked at so far, and so I'm going to show results for each of those 3. The first is risk scenario is the jamming of a message from a vehicle. So here this affects the vehicle directly, and so what we're going to also look at is how do the impacts change if we vary the number of vehicles that were affected from 1 to 5 vehicles affected. The second risk scenario that we're going to look at is that fake decentralized environmental notification message. So this is going to be affecting a roadside unit. And so it's sending out this fake message about hazardous conditions. And because it's affecting this roadside unit, what we're going to look at also is how the impacts change if you change the radius of your roadside unit and also change the number of roadside units that are affected. And we can see how the impacts change given these 2 parameters. And then the third risk scenario that we're going to look at is the forced sudden braking of a vehicle. So this is kind of a high-risk scenario where you actually want to cause a dangerous situation on the road. This scenario is going to be affected through the roadside unit, and so we're going to look at how the impacts change by how many roadside units are affected. And so the next few slides, I'm going to show the results for each of these 3 risk scenarios. So let's start with the jamming of the message from a vehicle scenario. And so we simulate this by changing the driver imperfection value and removing the vehicle's automation features. So removing the vehicle automation features is essentially saying if you're jamming the message, then you're not able to take advantage of the automation features. And so that should make sense. The driver imperfection value is related to the idea that drivers of vehicles with V2X capabilities and automated driving features have been found to have higher likelihoods of being inattentive or becoming distracted while they're driving because they're relying on the automation. And so then they also have a higher likelihood of making a mistake if automation fails. And so here we have an automated vehicle. We have the messages being jammed. And so the driver is going to be more inattentive and be more likely to make a mistake if that automation fails. And so here, the driver imperfection value in the simulation ranges from 0 to 1. 0 represents perfect driving, kind of a 0 chance of making a mistake. But in this case, we're going to increase the driver imperfection value from 0.5 to 0.9 to reflect this scenario. So let me go ahead and look at the jamming scenario outcomes. So here, so I have 4 different scenarios that are shown here. On the very left is the very left side here is the default scenario, and then 1 vehicle jammed, 2 vehicles, and then 5 vehicles that are jammed. And so what we see on the top are the distributions of the stop time, and then on this bottom plots are the distributions of time loss. And so you can see how the distributions change, and then the tables below show the actual numbers that we can get from the distribution like I talked about before. And so there's a lot of numbers here and a lot of different plots, but I want to draw your attention to the percent of vehicles affected here. And so compared to the default scenario, if you have a vehicle with messages being jammed, it actually affects 50% of the vehicles in the network. So 50% of the vehicles then experience some sort of increased time loss, increased stop time. In this case, there weren't any collisions, but they have this increase in time loss or stop time from this single vehicle being jammed. And so the kind of takeaways from these outcomes here is that the results affecting a single vehicle versus the default are noticeable. So we definitely have an increase in the number of vehicles affected. Half of the vehicles in the network are affected. But then if you look at between 1 vehicle, 2 vehicles, and 5 vehicles, there's actually a pretty small change there. So increasing the number of vehicles that are affected actually doesn't change the results too much. We will note that the outcomes and the impacts do depend on which vehicles are jammed based off of what its path through the network is. So you can imagine if a vehicle goes right through the center of the network, it might affect more vehicles than if it's going along the edges of it. So the vehicle choice does affect the scenario. And so, but overall, we see this increase in time loss and stop time for a large number of vehicles if we have even a single jamming scenario. But the overall effects are relatively small. The distributions look relatively alike. And so what we wanted to do in the next risk scenarios, and actually, so this is what this is showing, the other measures show pretty little change across 1, 2, or 5 vehicles. But what we want to show and we want to look at is actually impacting the roadside units, which will be shown in the next analyses, that instead of impacting a single vehicle, we can impact multiple vehicles at once. And we're going to see that these actually show larger effects. So let me go ahead and move to the second risk scenario, which is that fake environmental message there. And so this is, again, the idea of expanding a risk scenario from a single vehicle impact to impacting roadside units that impact multiple vehicles. In this case, the server sends a fake message, that decentralized environmental notification message, and then the affected roadside units then alert vehicles that there's ice on the road at that particular roadside unit's location, and then the vehicles receiving this fake message respond by slowing down. So this is a case where you might have an attack where then false information is being spread through the network. And so we wanted to see what the impacts of this false information is on the network performance and safety. So here, this are going to be the scenario outcomes. We're going to vary the radius of that roadside unit. So again, we have 4 plots here. We have the default scenario on the very left, and then we have what would be the impact if you increase the radius of that roadside unit from 50 to 200 to 400 meters. And so here we can see a very big difference. Let's focus on these right 2 plots here, the radius of 200 meters versus radius of 400 meters. So you can imagine, so this is the case where the roadside unit is affected, and it also then affects more vehicles because it has this larger radius that it communicates with. And so here you can see the distribution is totally different from the default and 50-meter radius distributions. We see that a bunch of vehicles on this very high-end time loss and stop time tail. So we have a bunch of vehicles with really high amounts of increased time on the trip and increased time that's being stopped. And so we see this is actually a pretty big impact here. And we can look at some of these numbers to see this. Previously, the mean time loss, and let's say look at the stop time first, the mean stop time is about 36 or 38%. When we have these high radius communications from these roadside units, the mean time loss and stop time goes up to 93%, up to 99% for the time loss for that largest radius. So we have these huge increases in the amount of time, stop time and time loss in the network. So we can see here, and the kind of takeaway here is that the large radius affects many vehicles, And so the shape of the distributions completely changes and the values also completely change. We can also see this from a few more of these measures here. If you look at the percentage of vehicles that are above that 80% threshold, so have greater than 80% stop time or greater than 80% time loss. So in the default and 50-meter radius scenario, we have, let's say, 3% up to 34% above that 80% threshold. If you get to 200 meters, we have pretty much 3/4 of the vehicles have greater than 80% stop time and greater than 80% time loss. And then for the 400-meter radius, we have over 80% of the vehicles have that very high amount of stop time and time loss. So we can see that impact is very large. And then the last thing that I want to draw your attention to is this last measure here, the vehicles that didn't enter the network. So this is counting the number of vehicles that didn't even have a chance to enter the network. And so the idea here is that the edges of the network are so congested, it caused such a big impact that a certain number of vehicles that would have been in the simulation actually didn't even have the chance to enter the network to start their trip. And so if we look at this 400-meter radius scenario, for example, we have 30.8% of the vehicles not entering the network. So almost a third of the vehicles weren't even able to enter the network because the network itself was so congested and there are so many vehicles everywhere, it didn't even have space to enter. So in this case, this is quite a large impact, especially compared to that jamming scenario. We can see how widespread one of these risk scenarios could be in terms of affecting the whole network. So this was varying the roadside unit radius. We also wanted to look at the variation in the number of roadside units affected. And so here we have those 4 plots again, but now we have the default scenario, 1 roadside unit, 2 roadside units, and 3 roadside units being affected. And so here we can let's look at the 80% threshold again. And so what we see here is that having a single roadside unit affected impacts the network. So we have definitely more vehicles in these higher threshold stop times and time losses. But one thing that we did find with this study is that the choice of which roadside unit is affected does impact the results. So this is something that we're continuing to explore here, but which roadside unit is vulnerable to the attack does make a difference in terms of how much impact that roadside unit has on the overall network. So to address this, what we wanted to do was actually look at some alternate roadside units and see what the difference in results would be. And so here, these are these alternate outcomes where we're varying the number of roadside units, but we're varying which ones are actually affected. And so here we have 2 roadside units, and then we have 2 roadside units with 2 different ones being chosen, and then 3 roadside units being affected, but then 3 different ones being chosen. And so what we see here is that if we look at the difference in the numbers between the 2 and 3, the numbers are actually not that different between 2 being affected and 3. And so this is suggesting that having additional affected roadside units has a smaller impact on the network than having that first affected roadside unit. So having just 1 roadside unit affected makes a significant difference, but having more doesn't necessarily, say, linearly increase the amount of impact. It doesn't just go in step in terms of the number of roadside units affected. But the other thing to note is that let's look at these 3 roadside unit and the 3 roadside unit alternate scenario. We actually have pretty different results here. So this is looking at that really high threshold, that 95% threshold. So this is saying that how many vehicles have greater than 95% stop time or greater than 95% time loss. And so this is kind of the worst experience for these vehicles in the network. They're pretty much spending the whole time stopped. They can't move at all, and they're losing pretty much all of their trip time because of this risk scenario. And we see that the number of vehicles or the percentage of vehicles that experience this is pretty different between the original 3 roadside unit scenario and this alternate scenario. And so we have a difference, for example, of looking at time loss between 2.5% versus 10.3% in that alternate scenario. So what this is telling us is that the choice of the roadside unit affected does matter. And so it can make a pretty big difference in terms of which ones are vulnerable or which ones are being attacked in terms of how widespread the impacts are over the full network. And then finally, I want to talk about this forced sudden braking of a vehicle risk scenario. So this is, again, going to be affected through the roadside unit with the idea that when a vehicle passes through the range of an affected roadside unit, it's altered so that it brakes harshly and unexpectedly throughout the rest of its trip. This is a pretty high-risk scenario that we wanted to look at here. And so it's forced to brake harshly every time it reaches a velocity of 25 miles per hour. And this would be a scenario of an attacker potentially wanting to cause a dangerous situation on the road. And so you can imagine this forced sudden braking of a vehicle is a pretty dangerous situation. And so we wanted to see what is the impact of this scenario on the overall road network. And so here are the outcomes for this forced sudden braking risk scenario. We have our 4 plots here again. So we have our defaults. We have 1, 2, and 3 roadside units being affected. And we can see, just looking at the distributions here, again, if we know that the right side of those distributions means that it's a really high stop time and a really high time loss, we can see between the default and just the 1 roadside unit scenario, the distribution moves completely to the right. So instead of having kind of this normal distribution in the middle, we have almost all the vehicles towards that high-end tail, which is saying that almost all the vehicles are experiencing a very high amount of increased stop time or increased time loss. And we see that for both stop time and time loss. And we see that for 1, 2, and 3 roadside units. We see that distribution shift over pretty drastically for this scenario. So we can look at some of these numbers. If we look just at that 1 roadside units number, if we look at all the numbers here, they increase very significantly compared to that default scenario. So our mean time loss and stop time go from 70% time loss to 98%, 38% stop time to 94%. We have 78% of the vehicles being affected in some way. The proportion of vehicles above those thresholds, so above that 80% or 95% threshold, increase significantly. And we also have a very high number of vehicles that aren't able to enter the network at all due to the congestion and disruption to the network. And so what we can see from this is that the impact of a single roadside unit being affected is large. If we look at, let's say, that highest threshold, so kind of the most severe case of vehicles being affected, that 95% threshold, the default scenario, it's 0 for both stop time and time loss. So no vehicles have greater than 95% stop time. No vehicles have greater than 95% time loss. In comparison with that 1 roadside units risk scenario, we have 46%, so almost half of the vehicles have greater than 95% stop time, which is essentially saying that they spent half of their entire trip just completely stopped in the network. Their trip has been completely disrupted. And then in the greater than 95% time loss, it goes from 0 to 83%. So 83% of the vehicles have greater than 95% time loss. So these are really significant impacts here with this forced sudden braking risk scenario. And then in comparison, the 2 and 3 roadside units being affected they don't increase the numbers by that much, but having just that single roadside unit being affected is enough to disrupt the whole network. And so in this case, for that 1 roadside unit, we see significant increases across all measures of these risk scenario impacts. And so we can see the impacts of each of these risk scenarios on these measures of network safety or network performance across these different scenarios. And so for this interdependent system case study looking at 5G with the transportation network, we have some overall conclusions that we can draw. The first is that the privacy risks are fairly contained. They're pretty targeted, so they only affect a few vehicles at a time compared to some of these safety and performance risks. And so if we look at these safety and performance risk scenarios, ones that affect vehicles on the road, ones that affect the roadside units, we can see that the risks affecting roadside units have greater impacts than individual vehicle attacks. That should make sense. The roadside units are able to reach more vehicles. We can kind of see that effect from a single roadside unit to multiple vehicles, and then those multiple vehicles then affect the other vehicles in the network. So we have kind of this cascading disruption that happens through the network, and we can quantify those based off of these different measures that we've looked at here. We can actually see the amount of increase that we might expect for any of these given risk scenarios. And then we did find that the impact depends on the specific vehicle or the roadside unit that's being affected. So the choice of roadside unit or the choice of vehicle does make a pretty big difference. And then the severity of the scenario as well makes a difference. So the forced sudden braking is kind of a more severe scenario than potentially sending an environmental message that's false. And so all these analyses enable us to get a quantitative sense of what the different outcomes of these different risk scenarios are. If there's any sort of attack or malfunction of the 5G network, how does that then translate into transportation network impacts? And so with that, I want to wrap up with some conclusions for this overall work. And so overall, what we're trying to do is we're trying to assess the risk of 5G. We want to provide a way to compare different risk elements and different risk scenarios. And we're doing this with a couple different approaches. The first is that we want to compare elements by different measures of risk impacts and try to be quantitative where possible. And so kind of making every effort to have a quantitative measure where it's possible. And so we're looking at, so this is the first part of the talk where I was talking about expected number of people affected, expected economic impact, probability of occurrence of an event, severity of the impacts, and then also the time required to restore full service. So we have these different measures that we can use to characterize these different risk elements and then do these comparisons across multiple risk elements. And then kind of shifting to the interdependent system and function is that we want to include risks across interdependent systems and functions. And so for our study, we've been looking at connected transportation systems. You can imagine doing a similar analysis for other interdependent systems and functions with the criticality of 5G for some of these operations. We see pretty severe impacts from the 5G network into potential dependent system impacts. And then for all of this work, what we want to do is to be able to quantify these impacts of these different risk scenarios, looking at different scenario types and different severity to be able to compare across different scenarios and across different risk elements. As I said, this is an ongoing project, so we are kind of continuing work in this area. Looking at those different risk elements, we're continuing to find reliable quantitative estimates of risk impact measures. These are sometimes difficult to estimate in terms of expected number of people affected or expected time to restore service, but we're continuing to build that out that full comprehensive view of the risk landscape. And then in that interdependent system case study, we are continuing to simulate additional risk scenarios and variations, potential combinations of different risk scenarios, different parameters that we can adjust and change to reflect different scenarios, and looking at the outcomes similar to the way that we've looked at so far to be able to compare which risk scenarios should we be more concerned about, which ones have the biggest impacts, are there different characteristics of different scenarios that lead to bigger impacts that we should care more about, with the idea that we can compare the different risk scenarios, identify which ones have the highest impacts, and then potentially do prioritization or comparison across those different scenarios. And so with that, I want to acknowledge students that have been working on this project. So Joseph, Kathy, and Paula Vargas have conducted most of the work that I've talked about today. I do want to thank the Department of Homeland Security Award through CIRI for support of this project. I have my contact email listed here. Thank you very much, and I'm happy to take any questions.
Please feel free to unmute yourself. We'd love to hear from you and ask your questions. We have some applause. Thank you. And again, if you don't feel like unmuting yourself, feel free to throw your question in the chat as we're monitoring that as well. Applause all over the place, Iris.
Oh, thanks.
Yeah. What's been interesting to me is to watch the evolution of this project and how you've been able to build out the risk scenarios and how that really has changed what you've been able to capture along the way, right? So that has been an interesting part to me to watch, and I look forward to seeing what those calculations and continued simulations will bring to this project.
Yeah, absolutely. I mean, something that we've found in working on this project and in this space is that like there can be very broad risk scenarios, like just stealing of information or having some sort of attack. But then it is interesting to go delve deeper into it and look at actually particular scenarios. What would actually happen if 1 versus 2 versus 10 are affected, or looking at those different parameters and how that can actually change the risk impacts pretty significantly if you go into those details there, for sure.
What would be the changes in the simulation with trucks, school buses, etc.?
Yeah, so we are only including kind of individual vehicles right now. I actually think it wouldn't be that different in terms of including trucks and buses. It would depend if they have any sort of, I think trucks are closer to the automation line than buses. Actually, the school buses maybe, but like maybe city buses might have some automation. I think the biggest difference would just be the size and length of it. But there are kind of safe distances that the vehicles maintain and braking distances that would be able to be incorporated. I think it would actually not change too much in terms of the overall scope of what the impacts would be. Potentially, you might have, if you have a bus or a truck being affected, you might actually have fewer following vehicles because there's just less space within a certain block or something like that. So that might affect it, but I wouldn't actually anticipate that big of a difference, including those types of vehicles in the simulation.
Is this directly applicable to anything, autonomous vehicles, drones, etc.?
Was the question, is it directly applicable to autonomous vehicles and other drones, etc.?
You got it.
Yeah, okay. Yeah, so what we wanted to do, definitely autonomous vehicles. So right now in the scenarios results that I showed, half of the vehicles are autonomous. So they are braking and communicating and maintaining distances through vehicle to vehicle and vehicle to infrastructure communication. So for sure, autonomous vehicles. I think one of the things that we wanted to do with this project is, as things are moving in this direction, it introduces potential vulnerabilities. If you're relying on that automation, then if that automation fails or if it's compromised, we wanted to see what the impacts would be on the network. And so even if the system were fully autonomous, if you had a vulnerability in the system that, let's say, sends that false message, for example, if the system weren't able to recognize that as a false message and actually sent that through, we want to see what the impacts would be on the rest of the system. So definitely applicable to autonomous vehicles. I could see potentially for other applications, say drones or UAVs or things like that. Similar analyses could be done where you have these, let's say, assets or individual items operating within a network, and then disrupting potential communication or responses between different assets could impact then how the assets perform, and then also potential other disruptions across the network.
And I don't know why my chat came in this way. Vincent's question popped up for Don here, and Don makes the comment that other areas of interest, automated UAV, examples packaging, delivery, network using cellular 5G. So there was that comment. Another question has come in as well. Will there be a follow-on study to assess cyber resiliency strategies? Example, multiple antennas on different bandwidths, performance tuning.
Yeah, I mean, I think that'll depend on a conversation between our group and CIRI and DHS and things. But that's definitely a direction I think that would make sense following these. So right now we're assessing the risks. Definitely the next step would want to be mitigation strategies and recommendations and seeing what we could actually do to decrease some of these risks. But yeah, I think that's absolutely right in terms of potential next steps and actually changing the parameters to decrease the risk. Right now, we're looking at the direction of kind of if something goes wrong, what are the impacts? But looking that other direction in terms of what could we do to actually protect against some of those impacts would definitely make a lot of sense.
Right. What about 5G interdependent industrial control systems?
Yeah. So I will say before we kind of went full on into this transportation network system, we were looking at potential other application areas. And so kind of overall, I think any sort of system or sector or function that relies on 5G, I would say would benefit from analyses of this type where we look at those interdependent system risks. So for industrial automation, for sure, I mean, the outcomes would be different. It might be in terms of safety, it could be in terms of faults in the resulting product that's being made. But I think in terms of broadly speaking, these types of analyses, I would say, are important to conduct, especially now as we're building out the system and trying to better understand what this type of operation would look like. Industrial automation and in manufacturing would definitely be, it was one of the ones that we actually thought about, and we decided to go with transportation systems, but that was definitely one of the application areas that is kind of one of the biggest areas for 5G for sure.
Just another minute here or so, and we have quite a few questions in here. Has there been publications, or are there plans for publications based on this work? I know you have one pending, but I'll let you answer that.
Yeah, so we are preparing, we have one pending, and then we're preparing a couple more related to some of the work that what I've presented today. Yeah, so we are looking to get those out as soon as possible. But yeah, we are preparing them now, and definitely once they come out, we would definitely be happy to share them. But they are kind of in preparation now based off of the stuff that I presented today.
Does the simulation and study take into account the usage of spectrum coexisting of 5G cellular NFCs other than telematics rely on?
So it does. I don't believe it actually considers what part of the bandwidth it's on. I think it's the parameters that I listed in terms of latency and in terms of packet loss and bit rate are the ones that we can specify in the simulation. I suppose you could kind of indirectly include some of those factors by changing some of those parameters that we input. But the ones that we're able to adjust and tune in the simulation are the ones that I listed in terms of bit rate, latency, reliability, and packet loss.
Other than simulations, are there other methods to explore the risk scenarios quantitatively?
Yeah, I mean, I think there are. I mean, it's a little bit tough. I mean, as we've been working in the space, since it is a new and emerging space, there isn't a ton of kind of really good, solid information out there in terms of operations and parameters and things like that. I mean, I could imagine something that's not simulation-based, like something that's more, I'll say from an engineering standpoint, like a more analytical way to do it. Like you could have equations that model certain types of outcomes and impacts. But it is such a new space that those haven't really been built out yet, but I could imagine that could be possible to do.
And I think, I'm sorry, I didn't mean to interrupt you.
I was just going to say, if more information were available, I would say.
Gotcha. And I think this is the last question here in the chat. Very well done. I like the organization of the content and scenarios. Would be great to see some of those future mitigation scenarios. For example, vehicles helping each other validate whether RSU message is accurate. Yeah,
absolutely. Yeah, that's something that actually me and the research team we just talked about recently was kind of if you have a fake message, if you have a conflicting message from another ROSA unit, which one dominates, which one would take precedence over another one. I mean, part of what I was thinking with that as well is I could imagine that if an attacker did send a false message, I could also imagine that same attacker having something written in there that would ensure that their message took precedence over other messages. And so I could imagine then also that even if there was some discussion among other vehicles and saying like, maybe this isn't a real message at all, if this isn't a real message, there could be other parts that are in that particular attack scenario that would actually still make that false message come to the top and be the one that the vehicle listens to. But there are all these kind of interesting permutations of these different risk scenarios that we're looking forward to looking more at.
Well, it definitely sounds like lots of more interesting data to come. We are at 3:03, and I want to thank you all for hanging around for our Q&A portion of the presentation. If there's a question that you have that absolutely didn't get answered, please feel free to email Iris, email CIRI. We're more than happy to facilitate and get you the answer to your question. And please look forward to our next CIRI webinar series. We'll be sending information out on that shortly. We do have a tiny little gap to accommodate for finals. So thank you all again for attending. and I hope you have a wonderful afternoon.